Hello, everybody. Today we're going to talk about dispersion forces. It's that dispersion forces, and I'm going to use the letter D to denote dispersion forces. Okay. So dispersion forces, London dispersion forces, London forces, Van der Waals forces, induced dipole interactions, they mean the same thing. And when it comes to dispersion forces, it is one of the three types of intermolecular forces. And as far as I'm concerned, this is the most important one as well, because this is common to any molecule, whether it is polar, non-polar, atomic, diatomic, polyatomic. They are there in all these molecules. Why? The only requirement for dispersion forces is to have induced partial charges. And how do we get induced partial charges? We get induced partial charges by disrupting or perturbing the electron cloud. So anything with electrons, which is almost everything, like atoms, molecules, polar, non-polar, anything, they have electrons. And if they have electrons or electron clouds, they can be perturbed by each other, okay, just by getting another molecule closer to one molecule. The electron clouds of each others will be perturbed, inducing partial charges, so inducing dipole moments in this molecule. Once you have induced partial charges, the opposite partial charges of nearby molecules or nearby particles can be attracted, and these are called dispersion forces. Okay, so now how do we represent dispersion forces? I'm going to use two examples to do this. So let's consider one non-polar molecule like nitrogen. Okay, let's say that this is one nitrogen molecule, and then so to represent interactions between molecules, you need to have at least two molecules. So here's another one closer to it. And to represent dispersion forces, we need to show the electron cloud. So we're going to represent our electron cloud something like this. Okay, so here are the two electron clouds. Now, just because these molecules getting closer to each other, that is enough for their electron clouds to be perturbed or disturbed. Once the electron clouds are disturbed, that means they're going to have induced partial charges. Let's say that we have a partial positive charge here and the partial negative charge here. They are going to be attracted to each other. Okay, because opposite charges are attracted to each other. Okay, and then let's say we have a partial negative charge here and the partial positive charge here. The opposite charges of adjacent or nearby molecules will be attracted to each other, and these attractive interactions are called dispersion forces. And keep in mind, dispersion forces are not just found in non-polar molecules. They are found in any molecule, even in polar molecules. For example, if we take ethanol molecules. Okay, here's ethanol, the line structure of ethanol. Okay, even that has an electron cloud. Okay, and when two ethanol molecules get closer to each other, that can perturb each other's electron cloud. Let me try to draw this here. Here are the electron clouds of one, and here's the electron cloud of the other one. Okay, just because they get closer to each other, that is enough for their electron clouds to be perturbed. And as a result of that, when the electrons move away from one side, and that that side is going to get a partial positive charge. Okay, and that partial positive charge can be attracted to the partial negative charge of the adjacent molecule, and that is going to give us dispersion forces. Okay, now these are examples. This is how we illustrate dispersion forces. Okay, now I already mentioned that the only requirement for us to have dispersion forces is induced partial charges. And how do we get induced partial charges? By polarizing the electron cloud, or by perturbing the electron cloud. Now, this one thing we want to define, like, roughly, that is the polarizability. Okay, because that is the important factor when it comes to the dispersion forces. So polarizability is the ability, okay, the ability to have induced dipole. So induced partial charges is called polarizability. Let's write that. This is called polarizability. Okay, and this is the main factor that determines the strength of dispersion forces. Okay, so roughly we can say that the dispersion force strength, I'm going to use D to denote dispersion force strength, okay, is going to be directly proportional to the polarizability, What this means is, if something is more polarizable than another, and that something will have stronger dispersion forces. This is what it means. Okay, and there are two factors that determines the polarizability, and those two factors are: one, the number of electrons, okay, and then the size. Okay, what is more important, the number of electrons or size, is hard to say. I mean, I cannot say that. But when it comes to predicting, we are going to stick with first the number of electrons, then the size, because we need to have some sort of system when it comes to predictions. But when it comes to explaining, it can be either number of electrons or the size that gives rise to higher polarizability. I mean, that's something we will explore when we talk about the examples. All right. Anyway, now how do we use this? So to do that, let's use an example. Let's consider let's say two nonpolar molecules, like say like argon and neon or something like that. Okay, because we know these are like nonpolar because these are just noble gas, right? Even they have dispersion forces. Why? They have electron clouds that can be perturbed to have induced partial charges, and those opposite partial charges of nearby atoms can be attracted to each other. So let's consider neon versus argon. Okay, now what we want to do is we want to determine which one should have stronger dispersion forces. To do that, we need to find out which one is more polarizable first. So what we're going to do is we're going to count the total number of electrons. Neon has an atomic number of 10, therefore it's going to have 10 electrons, and argon has an atomic number of 18, therefore it's going to have 18 electrons, and it's going to be larger as well. Obviously, argon is larger with more electrons, therefore it's going to be more polarizable. Okay, this is going to be more polarizable. Okay, if it is more polarizable, okay, then it's going to have stronger dispersion forces. So it's going to have stronger dispersion forces. Okay, now let's consider another example. Let's consider something like, I don't know, let's say HBr versus HCl. Okay, so these are polar molecules. Okay, so still what we want to do is, when it comes to dispersion forces, it doesn't matter whether they are polar or non-polar. What matters is the polarizability. Now, if we determine which one is more polarizable, that one will have stronger dispersion forces. That's the idea. Now, bromine has an atomic number of 35. Hydrogen is 1. Therefore, altogether, this is going to have 36 electrons. Okay, and HCl, on the other hand, chlorine has an atomic number of 17, and hydrogen is 1. So chlorine is going to have 17 electrons, and hydrogen is going to have 1 electron. Therefore, it's going to have 18 electrons. Okay, and we see that we have more electrons, and also it's going to be a larger molecule as well, right? Because HBr has more electrons, this is going to be more polarizable. Polarizability will be greater. Okay, therefore the dispersion force strength, D, will be stronger. Dispersion force strength will be stronger in HBr. Therefore, it's going to have stronger dispersion forces. Okay. Yeah, so this is how we determine the relative dispersion force strength using the polarizability. Okay, the idea is, again, the number of electrons, or higher the number of electrons, greater the polarizability, stronger the dispersion forces. Now, there's one other factor that affects the strength of dispersion forces, and that has to do with the surface area of contact. Let's consider two molecules. Okay, so what I'm going to do is, let's consider butane. All right, so here's butane, line structure of butane. We have 1, 2, 3, 4 carbon atoms, and then 3, 6, 8, 10 hydrogen atoms. Okay, and butane can have several, 3 isomers actually. So this is one of them. And let's consider another isomer of butane, which is going to look something like this. Okay, so just to understand what we have here, see, again, both of them have 4 carbons and then 10 hydrogen atoms. So that means both of them are going to have the same number of electrons. Okay, now I'm going to talk about something called branching in here. Okay, when it comes to the first butane, this is called the normal butane. You see that it's a linear molecule. It looks like a line. It's a linear molecule, no branching. But when it comes to the isomer on the right, okay, you have the main molecule going like that, and then you have a branch sticking out. Okay, so here's the implication here. When it comes to the first molecule on the left, okay, these types of molecules can get more closer to each other. Okay, as a result of that, let me show you 2 molecules. Okay, here's 1, here's 2. You see that they can get closer to each other. As a result of that, they're going to have a greater surface area of contact. But on the other hand, the right hand side isomer, because of this branching sticking out, these branches are going to act as a barrier for the molecules to come closer to each other. So here, so let's see that. So let's say that we have the same branch on this, like this orientation. Okay, you see that now these molecules cannot come closer to each other. The only part that is going to have some area of interactions is limited to over here, this small area. So in other words, you see that the branching causes the surface area of contact to be limited or to be reduced. Okay, so because you have a smaller surface area of contact in the right hand side isomer, is going to have weaker overall intermolecular forces or weaker dispersion forces in this case, because these are 2 non-polar molecules. Now again, to summarize, in these 2, if you compare these 2 molecules, let me try to write here. This molecule over here, cannot write for some reason. Okay, here we go. This molecule over here will have a greater surface area of contact, greater, let me write this here, surface area of contact. Okay, and as a result of that, it's going to have therefore it's going to have stronger overall intermolecular forces. Therefore, it's going to have stronger overall dispersion forces in this case, because only type of intermolecular forces we can have here is dispersion forces, and these dispersion forces will be stronger because you have a greater surface area of contact here. Now, just to complete this thing over here, what we started writing here, dispersion forces depends on the polarizability. Greater the polarizability, stronger the dispersion forces. Right. The other factor is the surface area of contact. Greater the surface area of contact, stronger the contact. Okay. Greater the surface area of contact, stronger the dispersion forces, right? Those are the two factors that affects the dispersion force strength. Let's have that in sort of a box. All right, so that's it. I hope this helped you review dispersion forces. I'll see you guys in class. Bye, everybody.